Alrighty, we're coming back to talk about machine learning basics. Okay, so before we talk about machine intelligence, maybe we should talk about human intelligence a little bit. Now, I think it's important to keep in mind that the human intelligence is kind of way different from machine intelligence in terms of the implementation and the way these are constructed, right? So obviously, computers are built off silicons and the internal logic is binary, is digital, and the human brain is analog. And if you look at the human neurons, they are absolutely different from what we call a neuron in computers, right? So the human neuron is biological. It relies on a lot of different chemical substances as transmitters between the neurons. I couldn't even name what those things are, but there's a bunch of chemical substances. Um, and the neurons live for a little while, but as all cells, they die and they regenerate and things like that, right? So all those things are different. So I would caution against simply equating human intelligence with artificial machine intelligence. I think recently we have seen some people there's a tendency in media, in newspapers and stuff, that people tend to kind of equate these things, and they will say, oh, computers, AI has acquired something that is just like human intelligence. I think these are things are similar in some ways in that they both rely on the processing of information. They cannot create information out of thin air. You have to learn from your observations and your interactions with the world. And those are things are similar. So from an information processing perspective, these are similar, but from the actual mechanisms, these could be quite different. And in terms of our ways to do experiments, with these two types of intelligence, obviously there's a huge difference, right? It's very hard to do experiments on human intelligence, but for artificial intelligence, like all of you can do it, right? You can always you can get a GPU, and you can do some experiments with artificial intelligence. So these things are similar in some ways, but I'm going to tell you something. I'm going to kind of tell you things like, they are similar in this way and that way, but I still wanted to preface that by saying, whenever you think about theories like that, you want to be a little careful. You can talk about it, but you wanted to understand what are the limitations of these theories instead of treating them as the absolute truth, right? So that's what I want to say. Now, having said that, I do want to highlight maybe some similarities between the human intelligence and the machine intelligence that we wanted to build. The human intelligence has an innate aspect and an environmental aspect. By innate aspect, I mean something that is passed on to us through our DNAs, through our genes, the chromosomes. And that is kind of what separates us from like other types of animals. And there are, make no mistake, there are some very intelligent animals, right? Like chimpanzees, dolphins, parrots. Some of these are well documented in the scientific literature that after some training, often intensive training, they can acquire a substantial level of intelligence, and often at the level of young children, like 7, 8, 9 years old. Okay, so chimpanzees, for example, you probably all heard stories about intelligent chimpanzees being able to do sign language and master like a few hundred words, right? So chimpanzees cannot really talk because of their particular biology. I'm not exactly sure what that is, but they cannot talk. And instead, scientists taught them sign languages, so they can gesture and they would tell you what they want, and they can do hundreds of English words. But none of these animals, no matter how hard you train them, no matter like you can train them since birth or something like that, and it's still not capable of reaching the human adult level of intelligence. So there must be something that is very special about humans, so that we can reach this level of intelligence. We may not be able to quite say what that is, what is that unique human characteristic, but we know there's something special about humans. Now, the second part is an environmental aspect. So what I mean by that is that you are this intelligent as you are today only because you have lived in the human environment, in the cultural environment for the past 20, 30 years, right? So we humans have designed sophisticated education systems to pass you knowledge that was accumulated over the past, I don't know, 5,000, 10,000 years, right? So Isaac Newton developed his theory of physics, and at that moment, nobody in the world has the same knowledge as him. But today, every secondary school student knows about, like, F is equal to ma, which is like Newton's law. Not because we're smarter than Isaac Newton. Probably we're not. Okay, but he came before us, and his knowledge get passed on to us, and we kind of build on their knowledge. We stand on the shoulders of giants, and that's why we are intelligent as we are today, right? So there is an environmental aspect and there's an innate aspect, and we want to make some analogies to the machine intelligence as well. And there is an innate aspect to the machine intelligence, which is to say, we want to design some things. Okay, we want to design. There are some parameters that are learned from data, and there are some parameters that are learned or not learned. They're predetermined by the human designer before any learning happens. And we typically refer to these as hyperparameters. Okay, so and these hyperparameters and the parameters and the input, they interact in some complex ways to create the prediction of the machine learning model, right? So the way these things interact is also predetermined before we let the machine learning begin, okay? So that's the innate aspect, which is to say there's some human design. And there is also the experiential aspect, which is like, how exactly do you learn the model parameters from data? Okay, so we refer to these as training. How do we do that? So that is kind of experiential, right? So we can differentiate between these two parts, and we'll see that over and over again. Now, what is machine learning? In particular, supervised machine learning. Okay, so supervised machine learning follows basically this formula, which is to say there is a function that we wanted to approximate. Okay, the function f has input x and output y. And we want to say, we know the function exists. And we wanted to be able to find the y that is corresponding to any given x. However, we don't know what the function really is. If we knew, we could just write it down. We could be maybe just sine x squared plus 5x, and that is equal to y, for an example. If you knew the functional form, you just write it down, okay? But it's often the case that we don't know what is the actual function. On the other hand, we have data. So we have examples. We know that, if my input is x1, my output should be y1. If my input is x2, my output should be y2, and so on and so forth. Okay, and the goal of machine learning is to, from the data exemplars, to find out the function that would work well on like data that did not appear in this training data, in this training set. Okay, so we call this the training set, and the function should work well on these, right? So sorry, the function should work on well on these, obviously, but also work on some test set that has not been seen during training. That's what we want to do, right? So that's kind of the basics of supervised machine learning. And you may say that this function approximation perspective is a little simplistic. You know, it seems to be something that we do in secondary school, you know, sines, cosines, like, you know, we know that stuff. They don't seem to capture anything intelligent per se. But I want to tell you that this basic function approximation approach actually works really well in the sense that it encompasses or includes a large number of real-world applications or real-world tasks that we would consider to be intelligent. And so I want to give you a few examples below. First example is automobile insurance risk, right? So if you have, you know, bought insurance for the car you drive, you may realize that, you know, the goal of the insurance company obviously is to make some money, and they make money by charging people on average more than they pay to cover the accidents the drivers get involved in, right? So basically you pay like, you know, a couple $100 every year for the insurance policy, and when you get into an accident, the accident could be worth a lot of money, it could be worth a few $1,000s of money. So how could the insurance company make money is that they have a lot of people who buy the policies, and on average, the risk of you getting involved in the the accident is pretty small, right? So in that case, you know, in expectation, the payout got to be less than the money you pay to buy the insurance policy, right? So the key factor here is to calculate what is the risk that you will get involved into in a automobile accident. And if you are a risky person, if you're a risky driver, you get into accidents a lot, I have to like charge you a higher premium. If you don't get into accident a lot, on the other hand, I should charge you a low premium in order to compete with other automobile insurance companies, right? Because if I charge you too much money, you will go away to a different company, right? So that's basically what's gonna happen, and it's critical to their business that they can estimate the risk of accidents accurately, right? So what can they do? For example, they wanted to collect a lot of information about you and about the car. For example, the make of the car, which is the manufacturer of the car, the model of the car, the year, any safety features, like collision avoidance and things like that. And you want to use these input to predict the output, which is like the probability of accidents you would that you would be involved in some accidents within a period of time, or how much money it's going to cost. But depending on the model and the make, you could some cars are very expensive, so the repair cost is also a lot. Now, so that's one example. Second example, heart disease diagnosis. All right. So when you have, heart disease and you go to a hospital, and they could try to give you a diagnosis, and they would take some information about you, your age, your gender, your chest pain location, and so on and so forth. And they wanted to like predict your diagnosis, right? So that's another one. A third one is image classification. All right. The input are the pixels of the image. So each pixel has three values: R red, G green, and B blue, right? So if you have, say, a 224 by 224 image, so then every pixel has three values. So that's your input. And your output is what object does this image contain? It could be a dog, a cat, an airplane, an orange, and so on. And then you could do some emotion recognition. The input is a snippet of text, right? So you could send a tweet on Twitter, and then the question is, what does this tweet reflect as the writer's emotion? It could be fear, anger, and so on, right? So these are all machine learning tasks, the real world problems that we care about, and they can all be captured in this function approximation from data paradigm. My point is that this paradigm is actually really powerful. It can do many different tasks, and even though it may seem simple on the outside. Okay, so if we want to analyze this a little further, we can look at the input and output, and we're going to look at the output. So depending on the output, we can further categorize machine learning into a few different applications, different types of machine learning. So the first one is known as classification. So in classification problems, the output is a discrete variable, and these classes are distinct categories. For example, you could have images, and it's one of these things, right? Dog, cat, chicken, duck, whatever. And you could have emotion categories such as fear, anger, joy, surprise. These are some commonly used emotional categories. All right, and these could be categories, and the point is that these categories are mutually exclusive. If you're a dog, you're not a cat, and they are kind of collectively exhaustive. It has to be one of the classes. You cannot say none of the above, or you could make none of the above a class that you consider, but you have to be a finite um, and usually a finite a category of things, right? So that's classification. Examples, you can classify handwritten digits from 0 to 9. You could, classify medical imagery. This is, an example. You can take a photo of your skin problem, and you could potentially send it to, a medical app on your phone, and it's gonna make a prediction or a diagnosis on what's the problem, right? So these are classification problems. After that, we have regression problems. In regression problem, the output is no longer just a discrete variable, it's a continuously varying variable. It's usually a real number, okay? So examples, it could be a stock price in a week. So you want to predict what is the price going to be in a week. If it's going to go up, I buy, right? If it's going to go down, I should sell. So that's stock price prediction. And heart disease could be treated as a regression problem, where if you say there's no disease, you would output 0. If there's immediate danger, if you're going to die, like, within a few hours or a few days, we're going to say it's immediate danger, and we're going to give you a value of 4. Okay. So now if you look at the second case, you may say, wait a minute. So I could treat this as a classification problem, couldn't I? Because these are distinct categories and there is nothing in between, right? You don't have like 0.5. For classification, you don't have like a half dog, half cat hybrid, That doesn't happen. Okay, so that doesn't happen in classification. So for this heart disease, also we don't have a category like half no disease, half mild disease. We don't seem to have that. So why couldn't we treat this as a classification problem? The answer is you could. Okay. So what is the key difference between measurement? What is the key difference between the classification and the regression problems? It's really in how do we measure the error. Okay, what do I mean by that? If the ground truth value, I'm going to say ground truth category or ground truth label is a cat in classification, my prediction is a dog, I have made one error. If my prediction is maybe chicken, again, I made one error. And if my prediction is maybe airplane, I have made one error. It doesn't matter which wrong label I predict, I make one error. For regression, that's a little different. It's because if my ground truth, say my ground truth is 1, and I predict 0, I can look at the distance between the prediction and the ground truth and I say I made an error of 1. However, if my prediction is 4, and I can compare that with 1, and I say I made 3 units of error, right? So we made more error, and we would rather do smaller errors than bigger errors. That's pretty intuitive. But the idea is that for real numbers or for these kind of problems with integers, there is a structure between the different predictions, right? There is distance between these values. And we can use that structure to give us some notion of error. Whereas in classification, most likely, there's no such structure, and every type of error is treated equally. So I think that is the key difference between classification and regression. All right. So besides classification and regression, there is another type of problem known as the ranking problem. So for example, if you use Netflix or Amazon, you have seen they recommend things to you. And it's not, they don't recommend a single item, right? They recommend a list of items. And as long as you like one of these things, you buy one recommended item, they would consider the recommendation being successful, right? So we don't necessarily care about only the first item, but the first n items. Okay, so that's ranking, and ranking is an important problem in practice, but for the purpose of this course, we don't talk too much about it. I just wanted to show you that these things do exist. So classification and regression are not the only form of problems that we care about in machine learning. Okay, so that is the end of machine learning basics. And once again, we're going to take a short break. And I'm trying to divide things into small units. So we're going to come back and then talk about linear regression.